Welcome everyone to a new seminar of the Research Division of the IAC. Today is a very great pleasure for me and I think for many of you to welcome Miguel Ángel Sánchez Conde back to the IAC. As you know, he did his licenciatura here like in the 2000s.
I don't want to remember. 2004.
Oh, you remember, right?
I finished in 2004. Yeah.
Then he went to do his PhD to the Instituto de Astrofísica de Andalucía.
Yes.
When he came back as a postdoctoral fellow, one of these postdoc genericos in 2009, I think. You stayed here for 1.5 years before you got an offer to go to Stanford to join the Fermilab collaboration.
Exactly.
A collaboration to which you have been engaged since then, very actively, actually, as I will mention towards the end of my introduction. Then he went for a postdoc to Oscar Klein Center before landing back to Spain in Universidad Autónoma de Madrid, Instituto de Física Teórica in 2017. So Miguel Ángel is a very well known expert in gamma ray astronomy, in particular focused on detection of dark matter, indirect detection of dark matter. And in particular, he also combines his expertise on gamma ray astronomy and astrophysics with numerical simulations. He's a well-known expert on the modeling of subhalo populations and how does this impact our prospect our own searches of dark matter. As such, he has been involved in all relevant collaborations, almost all relevant collaborations in gamma ray astronomy, starting from Fermilab, when he went to Stanford, but also in MAGIC and CTAO. As such, he has had leadership roles. In particular, now he's the analysis and physics coordinator of Fermilab, which is a very high position in the collaboration, very well-known collaboration in gamma ray astronomy, but he has also been in charge of the dark matter analysis working group of CTAO and MAGIC. Okay, without further ado, welcome, Miguel Ángel. It's our pleasure to have you here, and you please go ahead. The floor is yours.
Thank you so much, Jorge, for the nice introduction. I'm very happy to be here. Thank you for the invitation, first of all. I'm very happy also to explore synergies between your group and my group. More in general, I'm extremely happy to be back home, let's say, right? It feels really like home. So I just see in the audience many known faces, very good colleagues and friends. So it feels really like coming back home in some sense. I'm really enjoying also the island, trying to escape a bit from the Madrid winter, which is a bit too tough even for me. Okay, so today I will be talking about which is possibly my favorite topic these days. And it's basically the search for dark matter with gamma rays, but in particular from a particular kind of target, which we call dark satellites. And I will show you guys how, all our research line that we have been doing, all our efforts that we have been doing the last decade or so within my group to search for these guys and also to try to set constraints on the dark matter particle nature from this, and also to learn something about the underlying cosmological model. So let's start. I don't think I need to convince this audience on the fact that we believe that what we see out there in the universe is just a tiny fraction of the total content, the total energy matter budget, basically. Indeed, we believe that this visible matter is just the tip of the iceberg, right? Over, I would say, nearly 100 years now, we have been accumulating observational evidence of this need of non-baryonic form of dark matter at different scales, different astrophysical scales, from galactic scales up to galaxy cluster scales and cosmological scales. Of course, I'm not going to cover this in my talk, otherwise we'll be talking until from now to next week. Let me just say, just the take-home message, which is the fact that this evidence for this non-baryonic form of dark matter that we need to understand all this plethora of observations has been reported at all scales, as I've been saying. But not only that, it's only astrophysical as of today. It's something that I also repeat to my particle physics colleagues very often, because there's really nothing at the lab that makes us believe on this kind of non-baryonic form of dark matter. Everything that we know about this dark matter is actually all the motivation is actually coming from astrophysics. That's why I think astrophysicists like me and my group and many others in the world, of course, I really think we play a key role in this dark matter search. We have to be really cooking the whole thing. Okay, so despite all this plethora of observations at different scales, we have no clue about the ultimate nature of the dark matter particle itself. Unfortunately, the standard model of particle physics doesn't provide a viable candidate. Indeed, the only one, probably the neutrino, we know is not valid because basically it's too light to account for the total dark matter content. But as soon as you go beyond the standard model of particle physics, a huge plethora of possibilities arise that fulfill the requisites that we astrophysicists know for this non-baryon form of dark matter that I just leave here. Just to illustrate you guys our lack of knowledge, our ignorance on the nature of the dark matter particle, let me illustrate the point with this plot that you can see here on the right. And the x-axis, you can see the mass of your preferred dark matter particle candidate. On the y-axis, you will see something which is related to the interaction between these dark matter particles. And every box here will correspond to a different model, different model from particle physics that is able to basically give you a viable dark matter candidate fulfilling all these requisites that I'm talking about. I don't know if you guys are, are seeing this correctly from there, but there's something like 50 orders of magnitude in mass and around, let's say, 70 orders of magnitude in orders of magnitude, okay, in the y-axis. So basically, we know nothing about the nature of the matter particle. Basically the whole thing is widely open. It's too open, basically. It's the cross-sectional interaction between the matter particles themselves, basically. Yeah, self-interaction between the matter particles, yes. It's a bit more complicated than that, but it's basically that. Intuitively, it's really that. So again, every box here will correspond to a different set of models accounting for these requisites and providing you a viable dark matter candidate. For the remainder of the talk, unfortunately, because we have no time to cover everything, of course, I will concentrate only on this particular box, which is the WIMP, the weakly interactive massive particle, which for well-motivated reasons, I would say, our particle physics colleagues prefer and studied the most over the last decades compared to other candidates out there. These WIMPs, of course, fulfill all the requisites that we need for this non-baryon form of dark matter, and also is able to explain, to account for the whole dark matter content in the universe. So it has the right abundance, and it behaves nicely according to what we need, once again, okay? It's by far the most explored, the most studied scenario. So in that sense, the talk will be very standard, right? Because I will concentrate again on the preferred particle out there. Good. So when it comes to WIMP dark matter searches, people have put forward mainly 3 different approaches over the last decades. The first one is the so-called direct detection of these WIMPs. In this case, what you try to look is for interactions, very tiny, small interactions between your dark matter particles and ordinary matter at the lab. So there should be some kind of interactions at some level, right there. And by measuring the nuclear recoil, for instance, energy recoils of our ordinary matter, you should be able to reconstruct, to infer the existence of this dark matter. Needless to say, we found nothing for the time being, but our instruments at the lab are becoming very, very, very sensitive, and they are really putting a very, very good constraints on the properties of this dark matter, these WIMPs. Okay. The second method is the so-called indirect detection. In this case, you don't look for this for the matter particle itself, the interactions of the matter particle with ordinary matter. In this case, where there's so according to particle physics, to these WIMP models, the WIMPs are their own antiparticle in such a way that in large, in regions of the universe where there are high densities of these WIMPs, right? They will interact. They will basically interact between them, and they will annihilate each other. Because again, they are their own antiparticle, producing standard model particles as the final product of these interactions. Here you can see, how this change basically lead to either gamma rays, neutrinos, and antimatter in different forms. I will concentrate, of course, for the remainder of the talk, in the gamma ray, let's say, messenger here. Okay, and then the third approach that people have followed is the direct production in colliders of these matter particles. Provided that you reach very high energies at some point, again, you may expect the production, the natural production of some of these WIMPs in your collider, right? So this is also something that that people have been doing. Needless to say, there's a huge complementarity between the different methods covering different portions of the parameter space, right? So I really think we are in the same ship somehow, right? And we should really do our best to complement the searches and to talk each other among the different communities. Okay, so let's concentrate on the gamma ray regime, okay? This search for WIMPs with gamma rays. When it comes to gamma rays, fortunately, we have a very good battery of instruments working at the moment. In orbit, we have the Fermi Large Area Telescope from NASA, a mission that was launched in 2008 and is still nicely running. And as Jorge said, well, I'm particularly deeply involved in that. I'm the current science coordinator of the whole collaboration. So really involved. And then from the ground, by using a completely different technique, we have the so-called imaging atmospheric Cherenkov telescopes that you know, I think, quite well here, right? Because you guys are hosting MAGIC. There's also other two big collaborations here, HES and Veritas. More recently, we also have Hawk and LASSO joining the game. Also, the gamma ray astronomy world. Without really going into the details of the properties, the characteristics of these instruments, let me just say that they are nicely complementary in terms of energy range that each of them cover, basically, also spatial resolutions, and so on. So we are really doing our best to have the full picture by using data from the different experiments. Long story short, basically Fermilab allows you for all sky surveys, and also it operates in the GB regime, while Cherenkov telescopes and these water Cherenkov telescopes operate in the TB regime mainly, but they have a very narrow field of view. So you really need to know where to point the telescope. In opposition, as I said, to Fermilab, which has basically all sky. Well, in every pointing, it's like 1/5 of the full sky. In only 3 hours, we have the whole sky covered. And just a word in 10 seconds about the Cherenkov Telescope Array Observatory, of course, that you all know very well. This is coming. This is the imminent revolution of the field. Basically, there will be 2 arrays, one in Chile and another one here in La Palma, the Northern Array. And well, this is basically composed by telescopes of different sizes, covering energy ranges between the few hundred GBs, few tens of GBs, up to basically few hundred TBs even. Anyways, this is also coming. Good. So nice. We have a huge battery of instruments that we can use for dark matter searches. So now let's think about the different targets that we could explore in this context. This is coming from this picture here is coming from a numerical simulation, right? Just to understand which will be the main targets, the best targets for us. In particular, the galactic center is supposed to be the brightest one, given the proximity, and also, of course, that is a high dense environment in terms of dark matter, of course. But there are also different targets that one could explore for this search, and well, could try to look for. Unfortunately, we have been looking for this gamma ray dark matter signals from all these subjects over the last, let's say, 15 years, maybe 20 years or now. And to put the long story short, we found no signal at all. Although we have been, we had some claims of potentially, dark matter induced gamma ray emissions in the past. None of them survived, but one, which is the one coming from the galactic center. But that's another story, maybe another talk. Okay. So just to put the long story short, once again, no signals found. But that doesn't mean that we cannot do anything with that, of course. So we are basically restricting the dark matter models with these null observations of dark matter induced dark matter signals in the gamma ray sky. So let me just quickly introduce the typical tool that we have in the field to accommodate all these results, which is this one here. On the x-axis, you have the WIMP mass, basically the mass of your dark matter particle. On the y-axis, you have the cross-section of the annihilation between these WIMPs, right? And something also interesting to note is this horizontal line here, which is called the thermal Rayleigh cross-section value. which represents somehow our goal, where you know, basically the level of sensitivity that you want to reach with your instrument. The meaning of this thermal cross-section value is the following. You know, if you have a wind mass of this order and sitting here along this line with this annihilation cross-section, right, of few times 10 to the minus 26, you will be able to explain the whole dark matter content of the universe with the WIMP. That's why it's so relevant. So again, a WIMP sitting here will explain naturally, you know, the whole dark matter abundance that we need from the astrophysical perspective. That's why basically this is the goal. This is what we want to test. No? So you see different lines here. Every lines will correspond to an exclusion limit coming from different observations. Again, this is just a summary plot. There have been many observations from different targets. These are basically the main ones. Here you can see on purple, you have the Fermilab limits using dwarf galaxies of the Milky Way. As you can see, we're starting to rule out, oh yeah, by the way, everything is above these lines is excluded, okay? So these are upper limits to the cross-section. So again, Fermilab is able to basically rule out thermal WIMPs up to 10 GB or so. Now it's a bit better. This is from 2021, but again, it's quite okay. And in the TV regime, as you can see in the TV mass regime, actually Cherenkov telescopes start to be better. This is coming from Hess, for instance, from observations of the galactic center, the halo around the galactic center. And well, again, basically Cherenkov telescopes are better than Fermilab at the TV energies. This is again a very good illustration of the nice complementarity between the different instruments, as I was saying at the beginning. Okay, and by the way, as you can see, we are still far from touching the thermal radial cross-section values in the TV regime, and this is really something that we would like to have in the next years, right? Because again, it's the best motivated region of the whole parameter space. For WIMPs, for standard WIMPs, is something around 150 TeV. There are ways to go up, above these values. I'm not a particle physicist myself, but talking to my colleagues, apparently they can come up with some ideas to escape from this limit. This is what is called unitarity bound. Probably Jorge knows more than me about this. But the standard WIMP scenario is 150 TeV or so. TeV, yeah, mass. No, this is 1 TeV. This is 1 TeV, 10 TeV, 100 TeV. Yeah, that's why we are cutting more or less the plot here. Fabio, I think.
In the first introduction slide, when you show the WIMP box, it seems it was more narrow than this one, but this was a very. Is this the WIMP box that you? Is this a zoom on the WIMP?
It should be. I mean, I'm
not
sure if we are fully consistent with my box, but it should be.
But this is more or less expected in that range.
Exactly.
Okay.
The vanilla WIMP scenario is really here. The GB TV regime. Yeah.
Since we're asking, sorry, one more. In the previous slide, you said that when dark matter annihilates, it may give rise to gamma rays, neutrino, and antimatter. Is there any model? Is there any possibility that you don't emit any gamma rays at all? Could you have dark matter decaying or dark matter annihilating without giving rise to gamma rays, but just only neutrinos and antimatter? Or
you mean with WIMPs?
Yes.
Again, Carlos, I'm not a particle physicist myself. Maybe
Yeah,
can comment.
You will always produce secondaries, no? I mean, you have premenstrual and you will have always emission. Even if you produce, as soon as you have charged particles, they will be very energetic. They will have, but yeah. No, I think only in decay, no? If you have a decay of
in decay
an accident, you will have a line.
Yeah,
right?
I'm talking here about annihilations. That's true. In the case of WIMP decay, which is another possibility, you expect actually lines instead of this continuous spectrum from here. But I don't know any way to avoid the gamma ray stuff at the end. Yeah.
A question regarding your comparative plot of the cross-section bounds.
Yeah.
How are the systematic? I mean, I guess the different targets will have different systematics.
Yeah, absolutely.
In particular, the Milky Way is much stronger than
absolutely.
But you will have to fold in the modeling of the dark matter distribution.
All these limits rely on different assumptions of the dark matter modeling, the underlying dark matter distribution. I would say this one is quite robust. In my opinion, is the most robust limit that we have put so far in the field. the one coming from the dwarfs with Fermi-Lat.
Uh-huh.
The uncertainty on this guy is around a factor 50 or so when you change from cusp to core profiles and so on.
Mhm.
Doesn't really matter. But here it can be very drastic. The Hess observations, these Hess limits, assume a cusp profile for the galaxy, for the Milky Way, while it could be a core, why not? In that case, actually, you are not able to set a limit because of the strategy that they follow in the analysis.
Oh.
They wouldn't be able to even set a limit here. So yeah, take this with with a grain of salt, of course.
Thank you.
Okay, guys, I really need to speed up now. No problem, no problem. It's so, of course, very, very interesting, the whole discussion. Okay, so let's go back to this dark matter astrophysical targets plot, and let me now focus on the dark satellite stuff. Just leaving aside for the moment. Maybe we can take a coffee offline about each of these targets, but let me focus now for the remaining of the talk in these dark satellites, guys here. So what about them? So let me just go back to what basically our standard cosmological scenario, lambda CDM. And in this scenario, as you guys know, the less massive structures form first, and then by merging and by accretion, they will start forming larger and larger halos, right? Halos are basically the vitalized structures of that matter. So let me just illustrate the point that I want to make with this snapshot from embodied simulation, the G-Halo simulation, which was already performed several years ago by Joachim Staller and others in 2009. But still, again, well, indeed, it's the one, probably still the one with the highest particle resolution, pure embodied, no baryons at all, particle resolution in the market. So anyways, this is not so relevant. What is relevant is to understand the scales here. This is a Milky Way size cosmological simulation, which means that what you guys are seeing is basically of the size of the Milky Way. Okay, nothing more than that. As you can see, there's not the dark matter. Well, by the way, everything that you see bright here is actually dark matter density. Right? It gives you just a sense of the dark matter density. There's no baryons in this picture here. Okay? But the point I want to make here is that as you can see, the dark matter is not distributed within the object in a smooth way. It's not really a smooth distribution of dark matter, but actually it's very clumpy here and there, right? So just to put this figure into context, I just overimposed this sketch here for what our Milky Way would look like in this kind of picture. So we will have, of course, the baryonic material sitting in the very center of the whole halo, while there should be a huge halo surrounding the baryonic stuff, huge halo of dark matter, right? Again, not smoothly distributed, but actually clumpy, very clumpy. This is just a natural result of the way the structure formation works in lambda CDM, once again, right? You start forming first these small guys here and there, then by accretion and merging of these guys, you start forming a Milky Way size halo, for instance. So it's very natural to understand that there should be many subhalos, a lot of superstructure within larger halos. Again, because of the way lambda CDM works. Good. So we will have the so-called virial radius of the Milky Way, somehow at the characteristic radius of the Milky Way halo. And then within this Milky Way halo, we will have a lot of superstructure, a lot of subhalos. The most massive of these subhalos will, we believe they are hosting the dwarf galaxies, so visible satellites of the Milky Way, the dwarf, things like Draco, Ursa Minor, Sculptor, and so on, right? While there should be a huge population of smaller guys that wouldn't be massive enough to retain gas or stars at all, and there will be, basically there will be millions of them within the Milky Way virial radius, and we wouldn't know where they are because they are totally dark. It's just dark matter, no baryonic counterpart at all, right? I will refer to them as dark satellites from this moment on. Okay. Good. So these subhalos are actually, just a brief note about the potential that these subhalos may have to differentiate between different cosmological models. As you may know, I actually referred to that 1 minute ago. So this is a natural result of the way lambda CDM works, right? All these millions of subhalos, of tiny subhalos within larger halos, is just a natural again, a result of structure formation in lambda CDM. But there could be other cosmologies there, other cosmological models like warm dark matter, right? Where you have a cutoff in the matter power spectrum that prevent you to form, small guys. In the way that, you basically will have in this kind of world matter models, you will have the same substructure abundance above a particular mass to account for the observations that we have, in this mass range, like dwarf galaxies. You still have to explain them, right? So these world matter models will be totally fine at the largest scales, larger masses, while they could be very different at the smaller scales, in such a way that maybe you have much less abundance of tiny subhalos compared to cold dark matter. That really predicts a lot, millions of these small subhalos. So, well, probably you can see already the potential of these subhalos. If we actually prove that these tiny subhalos are actually there, this will help you to differentiate between cold dark matter and something else, to rule out, for instance, warm dark matter models, or vice versa. If, after many tests, we find that we are actually not in this kind of Milky Way size halo, but actually here, we will, well, surprisingly, we will be in a warm dark matter universe. So this is totally fine. Anyways, so this is what I want to the main point that I want to do here, right? That subhalos can be used as a cosmological test of the basically underlying cosmological model. But focusing on the gamma ray dark matter searches, let me emphasize the key role that these dark matter subhalos, these dark satellites could have for us. And not only dark satellites, but actually the whole superstructure. On one hand, you have dwarf galaxies and dark satellites being great targets for us because they are highly dark matter dominated systems. They are very compact and they have a lot of dark matter in there. So they will be by themselves great targets for our telescopes. On the other hand, all this clumpy distribution of subhalos within larger halos will boost your annihilation signal, importantly, very significantly indeed, because this annihilation signal goes as the square of the dark matter density. These guys are very compact, right? So you expect basically a lot of annihilation coming from them that will add to the whole annihilation coming from the whole halo. So this is called in the community superstructure boosts. And well, I won't have time today to cover this superstructure boost. It will basically be another talk I will be happy to give. But for the time being, I will concentrate today on the possibility to use dwarf and dark satellites as targets for our telescopes. In particular, of course, dark satellites. Good. I will say more in general that all these matter halo superstructure should be all over the place and is an unavoidable ingredient for dark matter searches at the moment. We are trying really to understand the key role of this dark matter superstructure and trying to implement the computation, basically the contribution to the dark matter annihilation flux coming from these objects for all the different targets. This is something that is happening at the moment, and it was not so obvious and so clear how to do it just a few years ago. Okay, so I think we really advanced a lot in this direction in the recent years. Very good. So, okay, so we want to search for these dark satellites. They have a great potential as cosmological probes. They have a great potential for dark matter searches. So let's go and look for them. How to search for dark satellites, since we cannot see them, right? There's no visible counterpart. So there are different approaches that people have followed in the last 15 years or so, I will say now. The first one that I want to briefly mention here is the strong lensing. I think the first papers in this direction came from Simona Beghetti and collaborators, as I said, 15 years ago or so, although there's been a lot of stuff going on recently too. In this case, the idea is the following. Basically you have the strong lensing effect, of course, and then if this superstructure is actually there, right? It's also sitting in the object that is acting as the lens, right? And therefore it should also add some distortions to your pattern, the pattern that you have in your detector coming from strong lensing, right? So basically you wouldn't have the same pattern from strong lensing in an object from a lens that has superstructure compared to the one that will be totally empty of superstructure. So the idea is to compare with thousands of simulations of the lens of the object that is acting as the lens, putting a lot of superstructure in there with different subhalo mass functions, different properties of the subhalo population. By using very sophisticated techniques, statistical techniques to compare observations with simulations, they infer the existence of this superstructure, and they are sensitive to masses down to 10 to the 8 solar masses or so. Okay, more or less. Actually, talking to Simona recently too, She said that it will be, well, although the future is bright of the future of the technique is bright, she's not so it's not so obvious for her that they could go lower than that. Maybe pushing, maybe they could go as down as 10 to the 7 solar masses or so, but it will be very hard to go below that to prove dark matter subhalos with even lower masses with this method. Second one, very cool one too, stellar gaps. In this case, the situation is the following: you have a stellar stream, usually a galactic stellar stream of in our own galaxy. As you guys probably know, these are thin tubular structures coming from dwarf galaxies or globular clusters that were accreted by our galaxy, and by very heavy tidal stripping, they were basically totally stretched, forming this kind of a stream of stars, right, in the sky, right? So the idea here is the following. Okay, so if there is a lot of subhalos, a very compact subhalos in our Milky Way halo, some of them will hit this stream of stars, imprinting some gaps, some peculiar gaps along the stream that we can look for, right? Again, this relies a lot on simulations, on our simulation work. Try to compare, observations of these stellar streams with, thousands of simulations, once again, of a Milky Way size halo with different subhalo population properties. By playing this game, Ray Carver, a theoretical guy that was basically putting proposing this kind of searches more than 10 years ago already, and others like Denis Erkal in particular, Bonac and others more recently, they were able to infer the crossing of the heating of these of tiny subhalos on some of these streams in the galaxy, well, down to 10 to the 6 solar masses or so. Although I would say in this case, for instance, there is some controversy because there might be some noise there, non-negligible amount of background to differentiate between these gaps and natural gaps that can be produced by other distortions in the galaxy. Okay, but anyways, this is a very promising tool to try to search for the existence of these dark satellites. We are also doing some stuff with some students in this direction now. Third possibility, which is the one that I like the most, of course, let's try to look for these dark satellites with gamma rays, right? Of course, in this case, you have a very big assumption here that, well, I'm a believer, so I want to believe that this assumption is actually true, but which is the fact that if the dark matter, of course, is made of WIMPs, then they will annihilate within these subhalos, and giving you, maybe, why not, a signal that could be detectable by our telescopes, right? Indeed, if this is true, maybe it could be the only way to prove dark matter, subhalo masses even lower than those provided by the strong lensing and stellar gaps. Provided that you have a dark satellite, close enough to the Earth, you may end up proving subhalo masses of, why not, 1 solar mass, 10 solar masses in principle, right? So it could be the only way actually to test even lower subhalo masses. And of course, well, this will be a huge discovery. It will also provide, of course, information on the nature of the matter particle as soon as we see a potential signal there that could allow you to extract the wind mass, cross-section, and so on. Good. So this is the question I had in my mind, not some years ago, right? So here in this plot, you can see something which is related to the annihilation luminosity, just to put it simple. Annihilation luminosity in the y-axis versus distance to the Earth on the x-axis for visible dwarfs, for the most massive subhalos that we know about. Okay, forget about this classical and ultrafine, doesn't matter. So these are basically a subsample, a very good subsample of dwarf galaxies that we are using for this kind of studies, for dark matter searches. We have been using them for 15 years now, and we know pretty well the dark matter content within the dwarfs. That allows us, again, to put a point here, basically to put some data here on the dark matter annihilation luminosity of these objects versus their distance to the Earth. Again, we know about them, we know where they are, and we actually can infer from kinematics, from star kinematics, the dark matter content. So this is pretty stable, pretty robust. The question is the following. Should we expect actually other satellite, for instance, sitting here, so very close to Earth, and giving you an annihilation luminosity even higher than the ones coming from dwarfs, which are supposed to be the golden targets for us in the field, and even more than that, no? Not only one, maybe how many of them are actually potentially detectable, knowing the sensitivity of our instruments to gamma rays? And even more, I'm going to be even more provocative. Have we detected them already? Okay, so this is the methodology that we're following to address this kind of questions. The thing is the following, guys. There's around 1/3 of the sources in every gamma ray catalog at the moment is actually, around 1/3 of the sources is actually unidentified. We don't know what they are, what these sources are. And this is not a small number. For instance, in the latest Fermilab catalog, the 4FGL-DR4, from the Fermilab collaboration, we have something like more than 2,400 NIDs, unidentified sources. Again, we don't know where they are. It's not a small number, right? Again, this is around 1/3 of the catalog. Please. Yes. Yeah, no, we catalog emission, so we have point sources, right? So we see them, we have emission detected by our instrument, right? But we're unable to associate this gamma ray emission to things that happen in other wavelengths, where there's no visible counterpart, visible, infrared, radio, whatever counterpart. There's nothing. It's not as simple as that. Indeed, what happens is the following. In gamma ray astronomy, we have angular resolution, a very poor angular resolution compared to other wavelengths, right? You can laugh about it. So it's around 10 minutes, 10 arc minutes, okay? This is our typical angular resolution, let's say. And what happens is that within this 68% containment region for the localization of the Fermilab point source, right? There's typically, okay, there can be tens of radio sources. There are a few X-ray sources, visible, optical, and so on. But there's no way, there's no univocal way to basically associate our emission to the emission coming from some of these other objects in other wavelengths. So that basically means that you are not able to associate once again, and therefore they will appear as unidentified in our catalogs. This is a fraction, the majority of them, I would say, especially in the galactic plane. In other cases, the sky fields are quite empty of visible counterparts and any wavelengths, and it's really a matter of something else, something that we really don't know. For instance, also they are usually very weak sources, and that doesn't allow you to extract, to derive a very good spectrum for them, and therefore you don't have the potential really to say, okay, this is an AGN, this is a pulsar, because basically, again, they are very faint, and they don't allow you to extract to meaningful conclusions at all. Actually, it's changing it. So there's been a non-negligible number of associations after Rosita for some of these sources, and some others I heard are on the way. So yeah, it's helping indeed. Good. So we have a lot of NIDs out there, shining in our Fermilab gamma ray sky, and we don't know what they are. It could be, why not? I'm a believer, once again, that some of these, NIDs could be subhalos actually annihilating into gamma rays, and we see this emission. But okay, let's try to prove them, or at least to put this at test. So what we have been doing is to build a series of filters based on what we expect from dark matter annihilation signal, and to apply these filters, quite technical filters that I'm not going really into the details in this talk. Again, to go through the list of NIDs and say, okay, this is compatible with dark matter annihilation, this is not, this is compatible, this is not, and so on, right? By applying this kind of sequential filters, by the way, we are able to basically end up with a much smaller number of NIDs that are compatible with being dark satellites. Possible results after all our methodology. Usually we end up with a few VIP candidates, which seem to be quite good in terms of spectral and spatial properties and so on. So they really survive our filters, and they look very nice. They really look like dark matter subhalos, right? For them, you may want to perform a more sophisticated data analysis, follow-up campaigns at other wavelengths, and so on. We are on the way. We have a few again, and we are doing our best for them. The other scenario is that you have a few more subhalo candidates, right? Okay, this is compatible, but it's marginally compatible, so you are not totally sure about them, right? They are not so good. But even for that, even for them, I will show you guys how we are able to use this information to set very valuable dark matter constraints on the dark matter particle nature. And the third scenario is the one in which you end up with no NIDs compatible with dark matter at all. So your filters are so good, you know, that in the end you end up with 0 NIDs compatible with dark matter. In that case, indeed, I will show you guys that is again it's a win-win scenario. Okay, I will really need to run. In this case, again, as I was saying, you will be able to set the best achievable constraints by using this method. So it's actually, again, it's a win-win scenario. It's the best that, well, it's bad news for the dark matter discovery. It's true. But on the other hand, you are learning a lot about the nature of the dark matter. So how we do that? Okay, we are relying a lot on our numerical simulations, both embody and hydro at the moment, right? So what, on one hand, from these simulations of Milky Way size halos, very high resolution simulations of Milky Way size halos, of course, you have all the information. You have dark satellite annihilation luminosities, right? The predicted ones. You know the number density, abundance, distribution, radial distribution, internal structure of the subhalos. You also know the spatial extension, right? So you know everything there. On the other hand, we compare all this information with the actual gamma ray sky, where you have your particular pool of NIDs. You have, of course, the instrumental sensitivity to gamma annihilation. We are doing a lot. We're being very careful on that. So by comparing this, by comparing the predictions with observations, we're able to set constraints on the matter particle nature. Just to put it simple, because it's a bit complicated, the way we perform these constraints compared to other constraints in the community, given the nature of the game. So imagine that we have, I was saying this for the same to Jorge yesterday. Imagine, guys, that we have, I don't know, 100 predicted subhalos that should be seen in the gamma ray sky, because again, you know everything, you know also the instrumental sensitivity. You end up with a prediction of 100 subhalos above the Fermi sensitivity, right? But you go to the actual gamma ray sky, to your catalogs, and after applying all these filters that I was talking about, you only have 50 potential NIDs, due to the matter annihilation. 150, this clearly allows you to set constraints. But even more than that, imagine that apply even better filters, and instead of having 50, I decrease the list to 20. And still my prediction is 100. So I'm being even, now more constraining. So the less subhalos, the less dark matter candidates among NIDs, that I have in the catalog, actually the better to perform the constraints. The best scenario, once again, in this kind of picture, is the one in which you rule out, you end up with the whole NID pool, right? As being due to the matter, and then you have the best constraints in the method. So this is now that we know about the methodology, let me show you guys a few examples of our results. This was performed by one of my students, Javier Coronado, years ago already, a couple of papers for that, where we look in the latest Fermi catalogs at that time. We ended up with order 10 VIP candidates, for which we perform also a dedicated spectral analysis that allows us actually to rule them out and improve the constraints, as I was mentioning. So let me just focus a bit and mention a bit these plots here. On the left, you have, again, this is a typical parameter space cross-section versus mass of the WIMP. And for different catalogs, every number will correspond to the potential, the NIDs that are compatible with dark matter annihilation, with being dark satellites, basically. For instance, for the 2FHL, we will have 4. For the 3FHL, we have 24. For the 3FGL, we have 16 potential NIDs, candidates, dark matter subhalo candidates. As you can see, we are not able to touch the thermal concession value, but we are actually providing very nice and complementary limits to in the field by using this method. Then, by performing that dedicated spectral analysis, a very sophisticated, more careful spectral analysis of the sources, we are able to rule them out, basically all of them, and we were providing limits which are really excluding already a portion of the thermal concession value at the lowest masses, and are nicely competitive compared to the best limits in the field coming from other instruments and targets.
Finally, after you're doing this spectral analysis, then your curves go down. They practically touch this horizontal line, which is
basically this one becomes the black line here.
Right, but then you have this parabola, which is blue dot dash, which is kind of
This one,
not the other one, the parabola that is
this other
some
one,
minima. Yeah, that one.
this is coming from Hess. So as I said, this is just to put into context, into the more general context, our limits, right? So we are basically comparing with the limits that I mentioned at the beginning from Hess for the galactic center halo, let's say, right? And also others like the dwarf galaxies with Fermi-LAT, and also even Planck by using this.
So naively, if I combine all those plots, then there is little room left for that you are not discarding, right?
Yeah, absolutely. Of course, we are there. So you mean all this part,
Yeah.
this portion here?
Yeah.
Yeah, absolutely. This is totally open at the moment. Yeah.
That's the only bit that is open so far.
Sorry?
That is the only area that is still not discarded by the data. If I interpret things correctly.
Remember what I said at the beginning about to one of your questions about Hess, for instance, right? I will take this with a grain of salt because they rely heavily on the particular form of the matter density profile for the Milky Way. I will take these ones are as very robust, while these ones are in a bit.
Okay, but you're getting there. You're in the ballpark
we are getting there
of discarding this WIMP.
Exactly. Yeah. Okay. So we went a step further after performing that first study. In a second study, well, actually a third one, a third paper, we actually wanted to explore also the spatial information. So up to now, to here, right? We're always assuming that our subhalos were basically point sources in the gamma ray sky. While by using by performing some simulation work, we actually realized that our brightest subhalos should be very extended in the sky. That doesn't mean that Fermi-LAT will see them as very extended, because that would depend on your sensitivity, right? The subhalos, the extension, the morphology of the signal is very peaked at the center of the subhalo, right? So it may happen that actually Fermi-LAT can only see the innermost part of the emission, right? So we wanted to explore that situation. How, a very extended subhalos, few degrees subhalo in the sky could be actually seen by our instrument, by Fermi-LAT. So we needed to convolve the dark matter signal with instrumental response. We did a very careful analysis, very, very heavy, careful analysis to end up with this kind of results, okay? What we actually saw is that the typical emission coming from the brightest subhalos in the gamma ray sky, in the Fermi-LAT sky, should be seen as a blob of 0.2, 0.3 degrees extension, no more than that. Again, you have maybe a subhalo of 7, 8 degrees, but only Fermi-LAT will only be able to see the innermost 0.2, 0.3 degrees or so, okay, when you convolve with the sensitivity. But this is very important because, of course, we were assuming in the previous works that we had the whole dark matter annihilation signal coming from the whole subhalo, while we are only sensitive to the innermost part, right? That we didn't account for that before. We actually did it here. We worsen our limits basically by using less annihilation signal, but of course we are having more robust results. So we are weakening our previous dark matter limits by a factor 2 to 3 or so, okay, due to this effect. Okay, I don't have too much time. I was hoping to have to show a lot of simulation work, but let me at least quickly go through that. Of course, guys, this is one of the main points that I also would like to emphasize today. All these results that I was showing rely heavily on our numerical simulation work that has been going in parallel, where we actually provide, well, we characterize with a lot of detail the subhalo population properties like the abundance, the radius distribution, the so-called concentrations, which are basically a measure of the internal structure of the subhalos. And by doing that, as I was saying, we end up with things like, okay, we noticed, for instance, that the low mass dark satellites could be as bright as the dwarf galaxies, right? Which helped us to understand the potential of the dark satellites for the search. Or also, as I was just mentioning, that the brightest dark satellites are supposed to be very, very extended. You can see up to 10 degrees or even more in some cases, right? These are the brightest ones, right? And well, but in principle, as I show you, we only see a tiny portion of that. So the simulation work is very important, not only to set the constraints, but also to guide somehow the search that we are doing and to optimize our search strategies. We have done a lot of work in this front so far in the last decade about many different aspects of the subhalo population, but further work is of course needed and ongoing. Let me just summarize at least quickly the main open issues that I think we have in the field at the moment. Of course, always with the purpose, with the goal, to use this as for our gamma ray dark matter searches. For instance, the subhalo survival is not well understood at the moment. Subhalo survival meaning to this tidal stripping, you may end up disrupting subhalos, right? Naturally, because of the potential, the deep potential well of your host. This is really not well understood yet. The role of baryons on this game, on how these baryons will change the subhalo properties. And also, well, we are also studying the structural properties of the subhalo and the evolution with time, which again will help us to put even more robust constraints. Jorge, you tell me, okay? Well, you stop me when in 3. Okay, great. I will do so. Thank you. Okay, so during the last years we are doing our best actually to address some of these questions within the group, in collaboration, of course, with some other people. Because again, we really want this method not to provide only constraints, but actually to provide reliable and robust constraints, no? Not only just very optimistic constraints or whatever, right? Things that you can really trust. So let me give you a quick example about the subhalo survival thing, for instance, that we have been working recently. The idea is the following. Since some time ago already, we know from hydro simulations that the role of baryons in this game is the following. You have here, for instance, from the fire hydrodynamical simulations performed by Xia, Garrison, Kimel, and others a few years ago. You have the dark matter counterpart of a Milky Way size halo, and you have here the same halo but with baryons now. We are, in both cases, we're only looking at the dark matter content, okay? And as you can see, there's a clear difference, a couple clear differences. In the case of the dark matter only case, you have a very round halo, host halo, while in this case it's oblate. And more importantly for us, of course, the abundance of substructure here is clearly, less than in the case of in the pure n-body simulation, right? So we are basically, apparently, what these authors and many others found is that the baryons, because they are sitting in the innermost part of the galaxy, they create a even deeper potential well. So you are more efficient to disrupt, many of these subhalos in the innermost parts. And this is actually what they see. They have a factor 2 reduction in substructure within the innermost 100 kiloparsecs, or even more, one order of magnitude within the innermost 25 kiloparsecs. So you better, accommodate and include this in your game before. The thing is that there are some other people that believe that this effect is actually numerical in origin, and it has to do with the resolution, the finite resolution of the simulations that you're using. This was basically put forward by Van den Bosch and others a few years ago already. Just long story short, there is a hot debate in the literature at the moment about this subhalo survival. Whether these tiny subhalos survive the potential well, the tidal stripping, right, in the host or not, which is, of course, very relevant for us. No? Maybe we are looking for dark satellites and they are not there, right? So you better are sure about that. So in a recent work by Alejandra, who's sitting there, my former student, now in Durham, and together with Raúl Angulo and others, and Go Guilla, what we did is to perform high resolution numerical simulations of subhalos falling into the potential well of a Milky Way size halo, right? We used millions of particles per subhalo, and under different orbital configurations, concentrations, and so on. And we took a look at the subhalo survival. We tracked the whole evolution of the subhalo down to present time. What we found is that for different configurations of these orbits and concentrations, basically, long story short, a remnant always survives. Okay, your subhalo will lose a lot of material due to tidal stripping, but in the end, you will always have some material, there's non-negligible amount of dark matter sitting there and floating around, and basically the subhalo survives. It largely depends on the concentration and orbital configuration, but as you can see, the bound mass fraction can be reduced by in some cases 99.9%. They lose all this material, but still this 1% is very important, especially for gamma ray searches. You have, as you know, you have a very Caspi profile there, and really what matters is what happens in the innermost part, which actually survives according to our simulations, right? So it's good news in general for our studies. And now I'm really concluding. So we did a lot of, we are also doing a lot of stuff, ongoing stuff, to understand the impact of baryons, the structural properties, the so-called tidal tracks. We are now working on that also with Alejandra. Let me just summarize here the whole thing and give some hints about where we are going at the moment. We are putting already dedicating observing proposals for these VIP candidates that we have among the pool of NIDs to understand really if they are still compatible or not with being the matter subhalos. We are also building more refined spectral and spatial filters for this, and performing also optimizing basically data analysis in these studies. We are already searching for distant satellites in brand new gamma ray catalogs. I didn't mention before, but actually we are already using the 4FGLDR4 with the help of Fernando Valenciano here to basically update all our work for the latest catalogs. We are, as you could see, we are performing brand new numerical work also to refine the whole predictions and constraints. We're also using machine learning techniques now to disentangle between astrophysical sources and dark matter sources, potential dark matter sources in the catalogs, like here, this work by my postdoc Viviana Gamaldi recently. And of course, we are planning to use CTAO, basically we already put some predictions for CTAO years ago, but we are really planning to use the first data also in our search for dark satellites, at least for the VIP candidates also to do some follow-ups. I stop here. I'm sorry for the slight delay, and thank you so much, guys.
Thank you very much, Miguel Ángel, for the very extensive detail and general talk that you have given us. Questions?
Yeah, thanks for this, stimulating talk. So,
thank you so much.
A very naive question: why is your predictions tied to WIMPs rather than any other physical process that just annihilate dark matter particles?
It's probably even more for particle physics. So I guess I got married to WIMPs because it's as I said at the beginning, the preferred candidate from particle physics, right? So it's the one that we starting to explore, and it's the one also that gives you, given the mass of these WIMPs, right? The annihilation products are supposed to be at this mass range, this energy range, GeV to TeV.
If you have an annihilation, I mean, I have no idea.
But I don't know what are the models.
If you have annihilation, it's annihilation of this mass, so you expect gamma rays given the mass.
Yeah, absolutely.
So it's not tied to
you have to have you have a model for other matter particle that is its own antiparticle. It has this mass, and therefore, in a natural way, right, motivates you the search in gamma rays, because you expect actually this kind of annihilation products for WIMPs. From other particles, I don't really know if you expect some annihilation too happening in gamma rays. There are other, just very briefly, there are other candidates, the matter candidates that could imprint gamma ray signals in our data. And we are also looking for that. For instance, axion-like particles. Didn't have the time, of course, but that's something, that's a different approach that we're also following within my group.
So we have this nice feature that you have a target, that is the thermal relic, the thermal cross-section. So you know where you have to go in order to exclude or discover the model. And typically also the WIMP was very favored by particle physics models because it is predicted. Yeah, will produce. Yeah.
Again, I don't know if there are such dark matter particles there too. Yeah. This strong motivation. Yeah. That's the so-called WIMP miracle. Yeah, Juan, please.
Well, I have a comment and a question. The comment is after your question. I mean, you had all this business 20 years ago about you expected the WIMP. You expected the WIMP at a mass of around 1 TeV. It was the so-called WIMP miracle.
Yep.
Okay.
Yeah.
So it was natural, like particle physics, to find it at this mass, but after the LAC measurements, I don't think it's so justified.
No, there's a lot of room.
There's always room for things.
Well, no, I don't think so.
Just a comment. Okay, but let me go for.
I asked it around particle physicists, many colleagues of us, right? And well, there's a hot debate, but I will say, from what I get is that there's a lot of room. Actually, the WIMP is really alive, still alive. That's not a problem.
Okay.
Not yet.
Then my question is a bit more technical. You were talking about if the subhalos could survive, and you concluded with your simulations, yeah, maybe 10% of the matter will survive. But I'm wondering, the subhalos you are looking for are those that are close to us, probably,
Exactly,
because
exactly.
those are brighter. And
Yeah.
are you? And those are the guys that go deep into the galaxy, and they must hit many baryons and yeah, exactly. So those are the ones that must suffer more from all these effects.
In our simulations, we took into account the baryonic stuff we have in the potential, in the description of the potential well that we have for the Milky Way. We are including the galactic disk, the bulge, and the gas. So that's really not a problem. I mean, we have all included. And as you said, they are the ones that suffer the most. Indeed, if you go to this kind of plot, right, that I was showing here, right, for some guys, depending on the concentration, of course, and the orbital configurations and so on, for some guys, the band mass fraction is basically untouched. But for some others, which are basically these ones, you end up with just maybe 1% of the total mass still bound. So they really lose a lot of material, but they are still there. And the main point here to understand that is really something that I was also talking to Jorge yesterday, I think, is the contrast between the compactness, the concentration of the subhalo compared to the one of the larger halo, of the host halo. A Milky Way size halo typically has a concentration of 10, 12, 15 or so, right? While in the case of these tiny guys, you are talking about concentrations of 80, 100, even more, right? Because of the moment where they were formed and the way the concentration evolves with time. So this contrast, this huge contrast between the compactness of the host compared to the subhalo allows you allows them, these tiny guys, to survive down to present time. That's really the key.
So, thanks for the talk.
Thank you.
My question is on the spatial distribution of the subhalos, and how do you translate that into predicted images of the gamma ray sky that you could measure?
Yep.
Because obviously CTA would have 5-6 hour minutes, but then from 5-6 hour minutes to tens of degrees, you could really explore the power at the different scales. And I wonder if you have already approached that.
Yeah, what we do is the following. I didn't really have the time to go into the details, of course, but what we do is we have a numerical simulation of a Milky Way size halo, right? But indeed, we do some we apply some bootstrapping techniques to end up with thousands of realizations of this possible Milky Way size halo, right? By, for instance, placing the Earth at different positions within, at 8 kpc from the center, right? By doing so, we are basically able to extract statistical meaningful results about what to expect, basically. It's not like we have a single picture of the distribution of the subhalos in the sky. We have thousands of them. So by statistically, looking into the details, we are able to derive by, like saying, okay, statistically you expect this number of subhalos within this particular field of view, things like that, right? For CTA, we did this work that I was briefly mentioning at the end with my former student, with Javier Coronado, and we actually were using the different pointings, expected pointings of CTAO in 10 years of life, basically, for whatever reason, right? So for other physics, AGNs and so on. So you have different pointings. We sum up all of them. We have a fraction of the sky, right? And we compare, how basically we calculated how many subhalos of these subhalos could be actually, in your field of view, in your accumulated field of view, right? And accumulated sensitivity too. Unfortunately, the constraints are not that good. They are not so, so good as good as we expected. But I think this is probably the way to go. We still need to refine the simulation work, as I said. But again, there's things that can be done in that direction for sure. Yeah. Carlos.
Me asking again. Sorry, I'm connecting to Juan's question before, which may be a bit technical. You said that even if 1% of those subhalos survive, they undergo tidal striping and so on. But I understand that the emission, what you actually measure, is depending on the concentration, on the density squared of the.
Yes.
So after they go through this tidal striping and so on, this is the
I didn't have the time. Sorry about that again, because I had to run, right? But this is this is the bound fraction after a ratio 0, right? And now you have how this translates into annihilation luminosity the ratio of the annihilation luminosity respect to the accretion time. So the initial annihilation luminosity that the subhalo had
That was the
when
question.
it was really a halo, still a halo, not a subhalo, right? So where you can see, for instance, for the larger concentration values of these guys, right? And some orbital configurations, very extreme orbital configurations, I would say, you end up with an annihilation luminosity which is basically untouched. But for those low concentrated subhalos, and again, the other way around of different orbital configurations, you may end up with just a tiny fraction of the initial annihilation luminosity.
And do you have any prediction where most of your subhalos are? Are in the high concentration region or in the low concentration region?
You mean the brightest subhalos
Yes.
that we?
Or the ones nearby, the ones you can.
No, we don't have it. That's a very good point. We will take a look. Yeah, thank you.
Thank you.
Okay, I think I'm afraid we have to cut the discussion here, but let
Very good.
us thank Miguel Ángel
Thank you,
again
guys.
for his
Once again,
wonderful talk.
thank you.
I think we still have scientific coffee or not anymore. Okay, then let's go. Let's go for coffee. Anyone who is interested in talking to Miguel Ángel anyways. Okay, thank you.